we're going to do today is we're going to talk about how we can test hypothesis using proportions. Now remember that proportions are generated from categorical variables. So this is really only useful when we're testing categorical variables. What I'm going to cover now is what's called a one proportion z-test. And I showed you some examples of these tests before. A two proportion test compares two different groups of things. So if you want to compare men to women, or blacks to whites, minorities to non-minorities, then you would be running a two proportion test. A one proportion test gives you a specified percentage, and then you compare the proportion to that specified percentage to see how unusual it is. So here's an example of what a one proportion test might look like. This is statistics from ISU that I gathered from a 2015 survey. And again, they do this survey across campuses in the US. The national average is 34.6 of students who reported binge drinking in the previous 2 weeks. Now for ISU, they sampled 586 and found that 45.7% of ISU students reported binge drinking in the previous 2 weeks. And so what we're interested in is testing whether ISU students drink about the same as the national average, or if this difference between 34 and 45 is statistically higher. We can see that it is higher, but we want to know, is this statistically different so that ISU is sort of an unusually high level of amount of drinking? The reason why we're interested in this question is because compared to other campuses, ISU students tend to believe that they use about the same amount of alcohol as other campuses. And so that's why we would want to test to see if these two numbers are different or if our perception is off. So to start off, we're going to assume that the ISU student population is the same as the national average. And then what we're going to try to do is collect evidence against that assumption. So we're going to assume that ISU is the same as the national average, and then we're going to try to find evidence against it. This is what's called our null hypothesis. And the null hypothesis always has equality in it. So it always has the equal sign. So if ISU is the same as the national average, this P for ISU represents the true proportion of students who binge drink at ISU. Now we don't know what that true proportion is. We're just assuming that it's the same as the national average. We haven't sampled the whole ISU population. We've only sampled 589 students. And remember that some of our samples are going to be greater than that true proportion, and some of them are going to be less than the true proportion. This one sample that we happen to sample is in fact greater than what we're assuming to be true at 34.6%. But what we want to test is this sample really unusual, or is it within a reasonable amount of variation to where this null hypothesis might be true? And that's how we're going to test this hypothesis. So remember that our z-scores are a measure of how unusual something is. So what we're doing when we're calculating a z-score is we're looking at our sample and we're saying, how unusual is our sample if the null hypothesis is true? So we're using this null hypothesis as our mean, and we're using that also to generate our standard deviation. So we're using the null hypothesis to create a distribution, and we're saying how unusual is our sample with this distribution. So our sample always goes first, and then what goes second is what our null hypothesis is, and then what we divide by is a standard deviation using that null hypothesis. So 0.346 times 1 minus 0.346, which is how I got this number. And then we also have to account for our sample size. Remember, there's variation in our samples, and so our sample size is going to affect that standard deviation. And so this is our distribution, and we get a z-score of 5.66. So we're going to use this z-score to create a probability for how unusual our sample is under this null hypothesis. So what we're saying is we want to know the probability that we would see a sample of 45.7 if the true hypothesis, if the true proportion for ISU is only 34.6. So how unusual is this sample if ISU is the same as the national average? You can see that this is equivalent to saying that our z-score is greater than 5.66. So the direction of the inequality is the same for both of these. And you can look this up on your z-table and you'll see that the probability is 0.0000, several zeros, and so it's highly unlikely that we would see a sample like this if ISU is the same as the national average. So there's two possibilities. One is that we have a really unusual sample. The second possibility is that we just made a bad assumption, and that's much more likely given this low probability. So because the probability is so small, we're going to conclude that the null hypothesis cannot be correct. So we're going to reject the null hypothesis in favor of the alternative. We have evidence to suggest that ISU is actually statistically greater than the national average. So we use our sample to test whether or not our null hypothesis is true. We use the hypothesized value to generate the mean and the standard deviation, and then we look at how unusual the sample would be given that mean and standard deviation. So the z-score is how unusual our sample is. If it's really unusual, then most likely we made a bad assumption, and we should state that we are in favor of the alternative hypothesis. We have evidence to support that. In the next slide, then, I'm going to break down how this hypothesis testing works into four pretty basic parts. The first part is to set up the hypothesis. That is how we figure out what the null hypothesis is and the alternative hypothesis is, because we're going to use that hypothesized parameter, the hypothesized proportion, to find our mean and our standard deviation, and then therefore our z-score. The model that we're using is the normal model, and that's step 2. So we have to verify that our assumptions are true. That is, that we've sampled randomly and that we have independent trials. And so just like we did before, we can test those assumptions. The mechanics are just what I went through in calculating the z-score. We're going to add to that then probabilities that we call p-values to make our conclusions about which hypothesis we have evidence in support of. So let's talk a little bit about these hypotheses. We have what's called a null hypothesis and an alternative hypothesis. Remember I said before, anytime you have a null hypothesis, you put the equals sign in that null hypothesis. And that equal sign is going to be your parameter plus some hypothesized value. So our parameter here is just the proportion. And then the alternative hypothesis is either some direction, so either greater than or less than that hypothesized value, or it could be not equal to. So here are 3 different possible tests that we could run. We could run a one-tailed test, which would indicate direction in the alternative hypothesis. So your question might say the true parameter is greater than the hypothesized value. That would be this statement here. If your statement is that the true parameter is less than the hypothesized value, that would be this test here. If there's no change or there's not the same, that's just going to be that they're not equal. And so that would be a two-tailed test. So here we have a couple of statements that we can set up alternative hypotheses for. So they're questions where we can set up both a null and alternative hypothesis. So this first question is just asking whether or not a coin is fair. And so we can designate that coin as fair if it lands heads 50% of the time. So P is our parameter of interest. It's just the proportion of heads. And we're just going to assume that it is fair. And so if it's fair, it should land on heads 50% of the time. If it's biased, then it's going to land either heads more often, in that case it would be greater than 50%, or it could be less than 50%, meaning it lands on tails more often. In either of those cases, it's going to be biased, and so we would just write not equals to in the alternative hypothesis. The next question we're interested in looks at the population's percentage of people who have obtained a bachelor's degree. In the 80s, it was about 14%, and we want to know if the percentage has changed. Now, we're not saying it's increased or decreased, and so the alternative hypothesis is that it's not equal, and in that case, it has changed. We're not saying that it's increased or decreased. That would indicate some sort of direction, and the statement doesn't say that. Our null hypothesis has the equality in it, so our null hypothesis is what we're assuming, that the population just has stayed the same. The last question then focuses on recycling rates, and a town passes a new mandate requiring everyone to recycle. And so they want to test to see if the recycling rate actually increased because of the mandate. So we're going to assume that it stayed the same as the hypothesized value of 0.25, and that's going to be our null hypothesis. And then we're going to go out and collect a sample and test to see if that sample is significantly greater than 25%. And then we'll have evidence in favor of the alternative, where the alternative indicates direction here because this problem states specifically that we want to see an increase in the recycling rate. The proportion here is just then the proportion of people who recycle. So that's how you set up a hypothesis. The null hypothesis specifies what you think that true population parameter is, even though you don't know what that true population parameter is, or that it's just too difficult to go out and sample the whole population. What we do instead is we just sample a small portion of the population and compare our data, our sample, to what we think that true population parameter is, that true null hypothesis. We can do this by finding out then how many standard deviations we are from the proposed value. So how many standard deviations that sample is from the true parameter, or our assumed parameter. We do this using a z-test then, as I stated before, and this is essentially how you do it. So in the null hypothesis, you put that proposed value, assumed value, and that is going to be used for your mean and your standard deviation. You can see the standard deviation is calculated using that proposed value. So the 0 here just represents that this is the null hypothesis value for the true parameter. And then the p hat represents your sample's proportion. So this null hypothesis here is just saying let the null hypothesis be for the true parameter equal to this hypothesized value. Once we have our z-score, then we can look to see how unusual it is and obtain what's called a p-value, and we'll do that in the next step. But before we get to that step, I want to talk about the assumptions that we're making by using this normal model and the z-tables. Again, we're assuming that we have randomized our data, our sample, and that we have independent observations. And these are the success, failure, and 10% conditions that you saw before. So these are not anything new. But again, when we're running tests, these tend to be where the most criticism comes from different statisticians, that your tests aren't valid if you don't meet these criteria, and they're pretty difficult criteria to meet. The last thing we need to do is we need to determine our alpha level. Our alpha level is essentially how much evidence we have against that null hypothesis. So if you think about a jury trial, in a jury trial, what the null hypothesis is that you're supposed to assume innocence until proven guilty. And so the null hypothesis being that the defendant is innocent, and then it's up to the prosecution's job to collect evidence, a large amount of evidence, to show that it's very likely that the defendant, is guilty. And so they have to show beyond a reasonable doubt, which you can think of as a 99% chance that the person actually committed the crime. And so these alpha levels are similar to that level of evidence that we're requiring. The more evidence that you require, the smaller the alpha is going to be. So it's more difficult to disprove the null hypothesis or to provide evidence against the null hypothesis with the smaller and smaller alpha level. We also call this alpha level the significance level. Once we have the significance level or the alpha level, we've determined that beforehand, we can compare it to our p-value to see if it meets our requirements. So, for example, the alpha level in a jury trial would be beyond a reasonable doubt. And so they have to provide enough evidence against that of beyond a reasonable doubt. In a civil case, where the plaintiff is suing for defamation or something like that, then the level of criteria is actually not as high. It's just a preponderance of evidence. So maybe it's more likely than not that the defendant committed the crime or the defamation. This p-value then is a probability. It's a conditional probability, and it's the probability that we see the sample that we do, the observed statistic, given that the null hypothesis is true. Now, I've provided here two misinterpretations of that p-value that are really common in the practice of statistics. So oftentimes in the medical field or even scientists will misinterpret what a p-value actually is. And this is because conditional probabilities are easy to switch around. But again, we're assuming that our null hypothesis is true, so that's what's given to us. And then we're looking at how unusual, how unlikely we would see the statistic that we do. The p-value then is just generated from our z-score. So once you've calculated the z-score, you can calculate the probabilities using the z-table. And how you do that is based on how you've defined your alternative hypothesis. That's why it's really important you set up this alternative hypothesis correctly. So if you're looking at something less than the hypothesized value, you're looking at everything below the z-score. If you set up your alternative hypothesis as greater than, you're looking at everything above that specified z-score. And so you can use these for the one-tailed tests. For the two-tailed tests, it's a little bit more complicated. You can look at everything above a positive z-score. That gives you half of the area, and then you just times it by 2. If you have a negative z-score, you're going to look at everything below and then times by 2. That's for a two-tailed test. So once we have our p-value, we compare it to the alpha level. So remember, the alpha level is sort of the standard that we're requiring from our evidence, and the p-value is the amount of evidence that we have, except that it works in reverse. The smaller the p-value, the more likely it is we reject our null hypothesis. So if we have a really small p-value, it's a really, really strange sample that we have, but more likely than that, we made a bad assumption and our null hypothesis is most likely not true. So if our p-value is really small, smaller than our alpha level, it means we have a lot of evidence against the null hypothesis. And so we would reject the null hypothesis in favor of the alternative. If the p-value is really large, greater than the alpha level, then we would fail to reject the null hypothesis, meaning we just don't have enough evidence convicting the defendant. It doesn't mean that the alternative hypothesis isn't true. It's just that we haven't collected enough evidence to suggest that it is in fact true. So our conclusions are either one of two things. We can either reject or fail to reject the null hypothesis. We never accept a null hypothesis and we never accept the alternative. We either reject the null hypothesis, saying we have enough evidence in favor of the alternative, that the alternative is most likely true, or if we fail to reject, then we just don't have enough evidence to suggest that the alternative is true. We're not saying the alternative is not true, just that we just don't have enough evidence. So for example, in the O.J. Simpson murder trial, the jury found that O.J. Simpson was not guilty. And again, they use the word not guilty because they're not saying we think that he's innocent, but rather the prosecution hadn't showed enough evidence that was beyond a reasonable doubt to suggest that the alternative, being guilty, was true. And so very much like a jury trial, that's what we're doing with these hypothesis tests. The last thing I want to really emphasize is this criteria for our p-values. We're going to learn how to run 4 different tests, and this criteria is going to apply to all 4 of those tests. So make sure you write this down and utilize it when you're doing any of your 4 tests that we learn. In the next set of videos, what I'm going to do is I'm going to work through a few more problems to show you how to set up a hypothesis and run a one sample proportion z-test.